Aryl diazonium salts in organic synthesis, preparation of P-Iodonitrobenzene and para-red. The purpose of this procedure is to prepare an aryl diazonium salt using arylamine and sodium nitrate. The aryl diazonium salt will be used to synthesize aryl iodide and para-red. Also to dye a piece of cloth that contains different types of fabrics with para-red. Examine the acidic and basic properties of para-red by analyzing the color and UV-vis spectra of the product obtained. Aryl diazonium salts are prepared by treating an acidic solution of arylamine, such as aniline, with sodium nitrate. This is a useful intermediate in the production of substituted aromatic rings. For example, aryl diazonium salts can be used to create iodobenzene. Aryl diazonium salts can also replace the N2 of a nitrile to form azo dyes by coupling and obtain products such as para-red. This coupling reaction results in an extended conjugated pi system. Systems like this are the base of colored compounds that can be used as dyes. Here we have the equation and mechanisms for preparation of aryl diazonium salt. Aryl diazonium salts are prepared by treating primary arylamines with sodium nitrate and hydrochloric acid. Generation of the nitrosonium ion is first. The nitrate ion is protonated once to form nitrous acid and then protonated again to form the nitrosonium ion. The nitrosonium ion can act as an electrophile and react with the lone pair on the primary amine of aniline. Protons are transferred from the nitrogen to the oxygen. Lastly, there is a loss of H2O, which generates the aryl diazonium salt. Aryl diazonium salt can be used to prepare para-iodonitrobenzene in the presence of potassium iodide. This reaction is a nucleophilic aromatic substitution. The iodine ion is the nucleophile, the aromatic ring is the electrophile, and the nitrile is the leaving group. The intermediate is resonance stabilized, and the product is an aryl halide. Aryl diazonium salt can also be used to prepare para-red in the presence of beta-naphthol. Here, the diazonium salt is reacting with another activated aromatic ring. This reaction, diazonium coupling, to form para-red is an electrophilic aromatic substitution reaction. The naphthol acts as the nucleophile and the diazonium salt is the electrophile. This results in a diazo-coupled product. Here, the intermediate is also resonance stabilized. The technique used in this experiment is UV-vis spectroscopy. This method looks at the electronic transition of a molecule between the ground state to the excited state, or the highest occupied molecular orbital to the lowest occupied molecular orbital, also known as HOMO to LUMO. Molecules absorb visible or UV light by promoting an electron from the HOMO to the LUMO. The wavelength of light absorbed is inversely proportional to the energy difference between orbitals. Energy equals Hc over lambda equals Hv is a common equation used to calculate the wavelength. The UV spectrum range falls between 180 nm to 400 nm and is shorter in wavelength than the visible spectrum range, which falls between 400 to 780 nm. The UV-vis spectroscopy plots absorbance versus wavelength. A compound must have pi bonds in order to absorb light. Conjugation and oxychromes affect your lambda max. Absorbance can be determined by Beer's law using the equation absorbance equals E times L times C, where E is absorptivity, L is path length, and C is concentration. The color wheel shows which color is visible based off wavelength of a compound. If a compound absorbs light in the 590 nanometer region, it is absorbing orange light. The color we see is a mix of all the other colors that are not being absorbed, and the compound will appear blue. Blue is directly across orange on the color wheel, which is how we know which color to expect.
In the preparation of P-nitrobenzene diazonium chloride, First, we must chill a solution of 2 grams of sodium acetate in 2 milliliters of water and 5 milliliters of 7% sodium nitrate. Second, add 0.3 grams of p-nitroaniline and 10 milliliters of water to a 50 milliliter Erlenmeyer flask. Stir. 3. Add 4 milliliters of 3 molar HCl and warm a hot plate. 4. Cool solution in an ice water bath for 10 minutes. Next, add the chilled sodium nitrate solution all at once, followed by stirring for 10 minutes, keeping the solution cold for the following steps. Label the beaker Diazonium ion, and then add the chilled sodium acetate solution just before its usage and the remaining steps. Production of P-Iodonitrobenzene. 1. Add 0.05 grams of potassium iodide to a medium test tube. Step 2. Add 1 milliliter of the cold diazonium salt solution to the test tube. 3. Mix till the gas is no longer produced. Step 4. Isolate the solids via vacuum filtration. Step 5. Transfer solids to a test tube and wash with approximately 1 milliliter of cold water. Step 6. Wash the solids twice as before. Step 7. Let the solids dry on a watch glass. And Step 8. Determine the mass and melting point. In the production of Para-Red, Step 1. In a 50 milliliter Erlenmeyer flask, add 0.1 grams of naphthol, then dissolve it in about 10 milliliters of hot water. Step 2. Cool the solution in an ice bath till it's around 5 degrees Celsius. Step 3. Enable the solution naphthol and keep chilled. Step 4. Transfer 3 milliliters of naphthol solution to a 10 milliliter beaker. Step 5. Quickly add 1 milliliter of cold diazonium salt solution to the beaker. Step 6. Stir. Step 7. Isolate the solids via vacuum filtration. Step 8. Transfer solids to a test tube, then repeat steps 5 through 8 from the previous step procedure. Step 9. Calculate approximate percent yield. Procedure of the in-grain fabric dyeing using Para-Red. Step 1. Soak the strip of 6 fabrics into a chilled naphthol solution, stirring as needed. Step 2. Remove the fabric from the solution and pat dry. Step 3. Add the damped fabric to the cool diazonium salt solution. Stir for a few minutes, then remove the fabric and rinse in a beaker filled with tap water. Data and calculations. Around 0.078 grams of P-Iodonitrobenzene was obtained, with a melting point between 160 and 163 degrees Celsius. This resulted in a percent yield of around 101%. This high yield could be the result of impurities. Around 0.06 grams of Para-Red was obtained, with a melting point between 238 and 242 degrees Celsius. This resulted in a percent yield of around 77%.
For the IR of para-iodonitrobenzene, the frequency at 500 we see Ci bond, and at around 1510 and 1410 we see a nitro group, and at about 1610 we see an aromatic ring. And for the proton NMR, there are 2 peaks which are both triplets of doublets, and the integration above 2. For the Colsey NMR, we see 2 distinct points which are 8.2 to 7.5. The 8.2 are the 2 protons that are close to the nitro group and they are symmetrical. However, the 7.51 would be the 2 protons that are next to the iodo group and also symmetrical. For C13 NMR, we see 5 peaks, which represents all the carbons on the benzene ring, and B and C are symmetrical. For the depth 135 CNMR, we see A, B, C 3 peaks. And comparing with the depth 90 CNMR, we see only 2 peaks, which are A and B, which shows that A and B are the carbons that are symmetrical and has a CH bond. For the IR, for pure red, there is a frequency at 1620 to 1450 representing nitro group, and 3385 representing the NH group, and also the one at 1590 representing the aromatic group. For the proton NMR for pure red, there are 6 peaks in total. For B, it has an integration of 3 and is multiplied. For A, E, and F, they are all integration of 2, and each of them have a pair of symmetrical protons. Looking at the COSY NMR for pure red, we see 4 distinct signals: 8.2, 7.8, 7.3, and 7.1, and which shows that 8.2 has 2 protons and is next to 7.3. For protons at 7.8 is next to 7.1. And these corresponds to the proton NMR in the previous page. Looking at the C13 NMR for pure red, there are 14 peaks in total. However, there are 16 carbons in a compound. The reason for that is that L and H, each of them are symmetrical carbon, so they represent 1 peak. For the depth 135 and depth 90 CNMR are the same. So for both chart, it would be 9 peaks. And the F and G represent the 2 different symmetrical carbons. For the UV-Vis spectrum, for pure red, before adding sodium hydroxide, the lambda max is 482 nanometer, the absorbance is 0.965, and after adding sodium hydroxide, the lambda max is 580, and the absorbance is 0.552. After adding sodium hydroxide, the lambda max increased to 580, which shows that it is more of a red color. And this is our bibliography. Thank you.